Well, Christos, thank you very much for the very, very generous introduction. I hope I can one day repay the honor of introducing you. So maybe Moody should arrange for that. And okay. Yeah. Very, very well, very well. So good morning. It's a great pleasure to be here. I would like to thank Professor Yaron Oz and Professor Moody Safra for inviting me here. And I think in case you don't know, I'm becoming one of you. I just received an appointment as the secular professor. So I look forward to coming here more and frequently. And so the topic I'd like to talk about today is Fintech. It's a very hot subject, and I'm not going to dwell on the commercial side of it, but rather I would like to focus on the science behind Fintech. And I think it's especially relevant here because University of Tel Aviv and indeed the whole Israel, I think, have more strength in the foundations of Fintech than almost anywhere else in the world. And to put the scientific foundation of Fintech into the right perspective so that we can appreciate better, I would like to start out by putting it against the backdrop of the very exciting time that we are living in, namely that the sciences are actually becoming, it was important before, but it's becoming even more important and transforming the world. And this is for all the sciences in general, and particularly for computer science. I think that in the last couple of years, almost every great computer scientist I saw, they would say it's a golden age for X, golden age, new golden age for computer architecture, new golden age for database, new golden age. So I think that we can say very confidently that we are really in a new golden age of computer science. And one particular aspect is about the interdisciplinary nature of the advancement and the breakthroughs. And so in this context, Fintech can be regarded as the meeting of minds between two really great sciences, the economics and computer science. And as we'll try to at least give some small illustration, that really in these great sciences, there are very interesting type of results, which really turn something which looks impossible into possible. And that accounts for why this kind of technologies, when it's possible to put into practical use, like now, are starting to change the world like never before. And then I'm going to talk about the content of the kind of using some illustrations, and then I will put it together in a small example about blockchain. And then I will conclude. So I think that it's by now, for the last few years, one amazing things after another appears. It shocks not just the scientific community, but appears in headlines all over the world. And so does this mean it's a new golden age for computer science? And the answer is emphatically yes. And how is it different from past golden ages? Because it seems that we have the personal computer revolution, the internet. Why this should be any different? And are there deeper implications that scientists and institutions should think about because of these fundamental changes? And my answer is still yes. First, let me just give one one very crisp answer to why I think it's different from the past golden age. And I think this is the phenomena of the role reversals. I think that in many traditional type of disciplines and industries, it's the specialists who would hire computer scientists for their purpose to do computation, to write software programs. But nowadays, we are starting to see there are many prominent professors starting biomedicine companies and using the AI technology as the foundation of the enterprise. And they would hire biologists to do experiments, carry out, going to the wet lab to help them. So this reversal is significant. It's not abstract in the science, but we'll see that it has big economic implications. And also, I think the institutions are realizing it. And I think the most recent example is that MIT has just created a college of computing, and they are putting $1 billion into this college. So I'm just copying from their news release that you would be the reason for doing that is that the digital fraction of the global economy growing much faster than the rest, and computing and AI are woven into every part of global economy. So they really want to go into this in a more systematic way, and to have more interdisciplinary appointments, because really it involves not just the information science, but involving almost all the disciplines. Now, on the commercial side, you can see that the big IT companies, they set very broad multidisciplinary agendas. If you look at Microsoft, IBM, Google, they all are interested in doing quantum computers, and some of them are doing life sciences and Fintech and autonomous driving. So these are the driver is information technology, and so I think everything fit. Namely, that it looks like that because information science is kind of progress very fast, and in many cases faster than the traditional disciplines. So therefore, it has reached the stage where the value of the added knowledge in the digital world, it becomes bigger than the traditional one. So it's this you can also see in the market value of the different companies. Okay, so I think that's I think it's a sign of this is a very new phenomena. And now I think that we want to look at, I mean, why is it that at this time that suddenly, just in the last 4 or 5 years, it seems that the world is really turning as regard to information science, and why now? And in my mind, really there are 3 different currents that happen to simultaneously become mature at the same time. So let me just kind of enumerate them. The first is that there's years of computer science research accumulations. I think that I got into this field probably around the same time as Christos, and well, I think Shafi. No, Shafi is much younger than I think. So in the early 1970s, I think when I think back, it's only within 10 years of the first computer science department in the world. So it's really a very young discipline. So the advantage of being old is that we went through all these years and can see how things changed. And now, computer science over all these years keep a low profile, and just happy to be of value to other science and the engineering discipline, and also to the commercial world. So, however, even though the outside world didn't really see much of what are the kind of a big, great, deep ideas in computer science, but they are all accumulating in different communities. And so after the 50 years, 40 years, then really we accumulate so much that, that especially in the theoretical way, that haven't been released yet. And so there's a lot of things that are waiting to be released if there is a application scenario. Okay, so this is kind of 50 years of computer science working. And the second is the maturing of interdisciplinary sciences. I think starting from the early 1990s, I think that probably the development of computational biology was a very good kind of landmark. I think that thoughtful people started thinking about, computer science. It's so essential. It's not just a very simple tool, but actually has some ideas in it. And initially, it was very hard going, that people spoke different language scientifically. But amazingly, that if you look at it now, then I think that there's a very easy communications between, for example, computer scientists and biologists. And so I think that right now, really, interdisciplinary sciences is no longer a novelty. There are many interactions between different fields, and in particular between computer science and biology, the physics, economics, and so on. So what this means is that there are other scientists who appreciate computer science in a much deeper way, knowing that there are things that can benefit the core of the other sciences. And so if they have some development, then they always think of that bringing the computer scientists along. So this is another stream. And the third one is that, I mean, so far, these are really academic. However, now, the last 20 years, there's this integration of science and industries and globalization. So everything becomes much larger scale. So whether it's in biomedicine, drug design, and automation, e-commerce, all these things now really can benefit more directly from the innovations in the sciences, in particular the computer sciences. So all these come together, and we are seeing an impact. For example, I've been attending this PCP test conference, and I think that many people are very hopeful, and I think they are right, namely that the making practical this kind of work is just a very short distance from having a major impact commercially in the world. And so now let me just show you some examples on these three streams that I mentioned. The first one is the quantum computer. The bases are in the computer science side, there are algorithms, there's architecture, and when it's coupled with quantum physics, and then it becomes very promising future directions for I think you would call it the post-microelectronics. I think it also, we are lucky at a time when the microelectronic revolution is coming to an end, that you have to deal with the quantum phenomena. And so, I mean, why don't we, instead of regarding the quantum limit as a foe, why don't we regard it as a friend? And the most prominent direction is the quantum computing. You really try to go even beyond the nanotechnology. You will try to be able to move atom, not just from one place to another, like in nanotechnology, but you want to move it from one place to another, keeping intact their quantum state. So that's another generation after the nanotechnology. And whoever controls the ability to manipulate these micro things will have a in a very strong position for the future industrial development. And the AI, I think that everybody knows, is starting from Turing, machine learning, and it's really it's coupling with all the disciplines and being applied everywhere. And the financial technology, it has its roots in the in game theory, distributed computing, cryptography, and it's coupled with the discipline in economics and finance, and now we are seeing very heavy growth in this area, and so I want to put fintech in the light of this, and I would like to talk about the science behind fintech as a particular case. And now, if you haven't been around, so what is fintech? It's just applying the advanced information techniques to financial services. There are two ways. One is to making the traditional services more efficient, like e-commerce, etc., or more importantly, introduce new services and platforms. And so the AI, big data-led market prediction, robo-advisor, and also everybody knows about the blockchain, and also in general the creation of even digital properties that you can manipulate and trade. It's something that wasn't here before. And now the science behind the fintech is the breakthroughs and accumulations in computer science, in the distributed systems, AI, big data, cryptography, and economics, game theory, auction theory, mechanism designs. And we'll look at some elements that are relevant for fintech. I think that there are so many cryptography things. I think that I think you have probably have participated in the PCP Fest and now Zero Knowledge. And so today we focus on the multi-party computation that Shafi also briefly mentioned yesterday, and also the particular case of the auction theory, and these elements will meet in blockchain. Okay. So now let's look at this in kind of these two elements, the cryptography and multi-computation. Multi-party computation is a concept that's proposed, I think, in the early 1980s, that allows computation to be done in an opaque way, that will not be, people will not know what the computation is, including the participants themselves. And using the multi-party computation, a number of servers can jointly compute any function without learning the inputs to the function other than the input themselves. So in particular, so when you can apply it to, for example, a group of people compute their average salary without anyone revealing her personal salary to the others in any way. And also more seriously, the multiple databases can jointly compute, for example, statistics on the combined database without actually sharing the details of the data. So you can see that the MPC allows us to do things for privacy. So individuals who care about their information stay private, as well as for commercial entities to protect their properties. You can see that big companies like Facebook and Google and so on, they certainly regard the data as wealth, and they hate to share it with others. Well, except possibly for a price, as we have seen in recent news. And so let me just give you a vivid example. So this is really the original example, it's called the millionaire's problem, and two millionaires wish to figure out who has more money, but without revealing any quantitative information. So essentially, Alice and Bob, two graduate students, one has X million, and the other 1 million, and they want to compute is X less than Y. Oops. So is there any way that you can, these two people sit side by side, and can you carry out a conversation at the end? You will get the information, but without revealing any other information. And now, any information theory students will tell you after thinking about for 20 minutes that it's impossible. You can prove that it is not possible. So the Shannon's information theory was the gold standard for security, I think even up to the late 1970s. Okay. And so if you apply that gold standard, then nothing can be done. Okay. Not millionaire. Essentially, any interesting internet applications we will not be able to do. But the more enterprising people would come up with a different answer, saying that, well, if it's impossible, maybe it's an opportunity that if you can make it possible. And so you have to think outside of the box. And now this is a very, very serious box because you have this great man, Claude Shannon, built this cage, and you sit in it. And now, how do you get out? Well, if you look around, you see another giant, Alan Turing. And if you seek the help of Alan Turing, then you successfully slip through the cages. and so that's what happens. I don't think people initially thought in that fashion, but this is really what happens. You have these two great scientific disciplines, and they were separately like two different islands. But there is this opportunity, the Diffie-Hellman and the public key suddenly make it inescapable. You have to put these two things together. And the revolution is not done yet. I think that the merge is not perfect. But essentially, information theory and computation theory should be in one big whole. Okay, so let me just show you how this can be done. Okay, metaphorically, Alice gives Bob n sealed envelope. Say n is the number of millions maximum you can have, and you want to and so in two sealed envelopes, and so the initial x will put a 0 in it, and the rest will put a 1 in it. And now Alice turns her head, and Bob picks out the envelope number y to see whether it's a 0 or a 1. And then if you can do this, then you solve the problem. And of course, the challenge is that how do you do it electronically using encryption? And well, so I think that you see the thrust. You just implement the sealed envelopes using a separate private key for each envelope. So Alice is going to prepare these envelopes and create the keys. And now Bob doesn't know any keys, so cannot open any envelope. So Alice sends this to Bob. And the second step and the third step, you use an oblivious transfer, so that that using this method, Bob can get a key number y from Alice without revealing y. And also the cryptography can make sure that exactly one key is transformed. So the oblivious transfer is allow this to happen. It's a Michael Rabin invented this concept, and so this can be done. Okay, so the solution that described can be extended to any computation by a circuit. I think that the envelope thing is too cumbersome and exponential inside. So really, you should use circuit and encrypt each circuit in this way, and this is now called the Gobble circuit method. And I think that the multi-party computation has become a pretty large subfield in cryptography for the last many years. And since I think that there are 3 initial pioneering papers in this area, and including one, Goldreich, Mihaly, and Wichter. Somehow, I have the feeling that every author I quote, some of them will be from Israel. And many advances have been made for this almost kind of 35 years in the implementation of system, especially in recent years when people realize that that this is something that the world needs, that the big data entities, they like to be able to share data, but they want to protect the data too, okay? Now, so I think that the progress has been phenomenal. I think by now, especially in recent years, you can see that over the naive implementation, it's a kind of I think it's at least a 5 order of magnitude in terms of speeding up. And so now it's really close to becoming practical even for very general computations. And now there are many application scenarios you can think of, but let me just mention one that's a very serious application. There's a paper by it's Bonnie Berger's group at MIT. They published a paper recently in Science, and so it's just giving detail of a collaborative platform to allow the biomedicine different groups and hospitals. They will be able to share their data because the purpose for this each of this group is really to use the machine learning method to find good pairing between the drug and the kind of the targeted disease. So if you can put resources together, you get better statistics. You get the AI will give you a more efficient outcome. But everyone still wouldn't want to review their data. So how can you carry this out? And so this now actually is becoming possible. So it's not just the fintech. It's really also for science and other applications or government purpose things to protect privacy and data. And I believe that cryptography knowledge like that, the multi-particle computation and zero knowledge and the PCP test, I think this will, over the next few years, is going to rival kind of the popularity of Bitcoin when these things actually becomes more readily available. Okay, so now I'm coming to economics. Okay, so so let me just start talking about auction. The bidders will submit the sealed bids without knowledge of other people's bids. So the simplest mechanism is the highest bidder win. And now this, if the highest bidder wins and pays the bidding price, then the highest bidder usually want to share their bid because they think other people may not bid as much. And now another alternative is very clever. It's saying the highest bidder wins, but the price paid is the second highest bid. The second price auction by victory is different from mechanism 1 in that it gives bidders incentive to bid their true value, so they don't have to lie, because lying is not to buy you anything. And so this is called incentive compatible mechanism. And you may ask, why do we really want to have incentive competitive mechanism? So let me say that it's not because the economists are more ethical than we are. I think that there's a theory behind it why this is a good thing to do. And now the theory of auctions behind on game theory, and when you think about it, I think it's a pretty miracle. I think that if you have not seen anything, it just tells you there's a very big economic system, and people have very different incentives and agenda, and how do you organize the system? What would be a way to figure out a good way to organize the economic system? And however, there's a miracle that somehow game theory allows you to at least take a guess, a plausible guess at something, to have some resemblance of reasonableness. And so each player will use some strategy to maximize the gain at equilibrium. And in game theory, they are interested. They're saying that we don't know the dynamics, how you get there. But it's quite plausible that rational people, when they are using their strategy in such a situation where they cannot benefit from switching their strategies, that may be a possible outcome if you set the rules in a good way. And so the game theory founded by von Neumann and Nash. So I think it's really it's really one of the intellectual triumph to organize the world. And now, so there are 4 people on the slides. I think 2 of them have a Nobel Prize, and I think the 4th one doesn't need a Nobel Prize. And now let's put in the millionaire's problem into this context of auction theory. So in computer science, we say that Alice and Bob know what they have, X and Y. All we want to do is to make the interaction so that they will not reveal their values. Now, you can interpret this in auctions, right? Alice has something want to sell. The minimum amount is X million, and Bob has Y million. And now, in this case, the interpretation is that they want to decide whether they can make the deal, whether Bob's price is bigger than Alice's price. And now, however, the requirement on what kind of protocol you use, the requirement is different. For multi-particle computation, you only need to prevent leaking of private data. So everything is just computational. You have very well-defined function. You do this, but in the case of the auction, and presumably the auction not only would determine whether Y is greater than X, but how much Bob actually pays Alice. Okay, so now the auction, you would like to design it in such a way that Bob has no incentive to not speaking the truth. And as I said, that why are we insisting on requiring the Bob to speak the truth? It's because of the game theory I talk about. It's saying that there's a reduction that says that if you adopt the philosophy that equilibrium is the point where you can discuss of the economic outcomes, there is a transformation, an easy transformation, which says that without loss of generality, you can assume that the mechanism is defined in such a way that everyone speaks the truth. Okay, so that's an enormous simplification when you think about the complexity of designing to wanting to find equilibrium, because this is a much smaller space that you have to search through, and that's the reason why the economists the auction theorists are interested in restricting to the truthful auctions. And so just look at it, that to summarize that the multi-party computation, you have n parties holding individual data. You want to compute the function and preserving the privacy. And the economics, you have n rational players in the market, each with their own agenda and utility, and they want to jointly to maximize certain goals. And that's the purpose of designing the mechanism, is to make it to maximize the social welfare, to maximize the revenue and whatever objective one wants to have. And so in auctions, you want to maximize revenue through incentive compatible, truthful biddings. And there's a rich theory so that if we need to design some auction along with blockchain or others, then we have some foundation so that we can discuss. And now in auctions, the simpler case is just one seller and one item to sell to a buyer. And so this is a very standard setup where the seller has a partial knowledge of the buyer's interest as captured by a prior distribution F. And how does the seller maximize the revenue? Well, it's just to maximize the point X such that the expected value to be maximized. And the the game theory saying that you can, this is the best you can do, no matter what kind of sophisticated thing you get. Now, selling one item to n buyers, Meyerson gave an elegant and complete solution for general n. It's a very non-trivial thing. I think that it's when we think back, I think it's pretty amazing. In the 1980s, at Berkeley, when I was with Chaffee and Civil, and there's somebody also is thinking about this multi-party computation, but it's for a different purpose. And when you look at what Meyerson had done, and if you don't tell me, I would say that this is a very brilliant theoretical computer scientist and formulating a great problem and having an ingenious solution. And so auction is a place where the theoretical computer scientists have got into. I mean, not just auction theory, but the mechanism design and other things. But for the last 15 years or so, that there's a community of theoretical computer scientists who does this, so now what did theoretical computer science contribute to this collaboration with the economics community? Well, I think that the main thing, I think that there are two things. One is to inject some new concept into the study and seeking to understand economics from a new angle. So, for example, economists know that multi-item is hard. They don't find any good solutions to it, and we supply the reason why it's hard. It can be shown to be NP hard, and so therefore, what this actually means is that if you think in the language of the economists or the kind of operational research people, is that the landscape for this problem. So you have the instance of the auction, and you have the optimal value revenue you can get. It's a very complex, kind of a multivariable things. It's being NP hard means that we don't have a good way to simply characterize it and find a efficient algorithm to figure out what the optimal solution is. So I think this is one easy contribution. Now, together with this, computer scientists, when they face with NP hard problem, they say we do approximation algorithms, and also this is the PCP is so famous for. So this approximation paradigm, it can reveal patterns in the landscape. I mean, not in the very detailed one. I mean, if you insist to be very exact, you want to find out what happens near the optimal point. You will not be able to do it because it's NP hard. But approximation means that if you look at it with a coarser scale, then you might be able to figure out patterns. You can see that if you don't use such a fine microscope and you look at in the aggregate, for example, if you look at it in the logarithmic scale of the revenue, then essentially, that the constant approximation means that you only differs by a constant. It's the optimal. Okay, and now approximation paradigm, it not only will give you some kind of approximation algorithms, but in the process, it will give you information about the structures. And therefore, now you can ask economic questions. The economists, because usually if something is not very exact, they will give up. They will say that, well, we know some natural things is not true. But in the approximation paradigm, we go further and saying that maybe it's not precisely you can get this property, but is it true, more or less? And so at least for the computer scientists, this gives some insight into the economic question. But whether the economists kind of think it's important or not, that I cannot say. And but the theoretical computer science algorithm, our techniques can also contribute to address classical issues. For example, whether the Bayesian and dominant strategies are different in some specific context. Okay. So, so I would like to just give a sense on what the theorists have done. I would just focus on, there are many papers and many great papers Crystal have written about auctions and other algorithmic game theory problems. But let me focus on something that I know well. This is a line of work that started in your kind of brother institute at the Hebrew, Hart and Nissan. Asked this question that what's in approximation algorithm, what's the best you can do? And also, I think they stress 2 points. One is that they would like it to be putting no assumptions on the distribution. They would like the result to be general. And secondly, they would like to ask structural questions, saying that can we, within the approximation paradigm, can we say something about economic issues? And so using this method, computer scientists have been able to design constant approximation algorithms for the one buyer case, and then for the n buyer, and there's a lot of interesting machinery that turned out to be relevant for this design. And in the process, it gives us information about the landscape of the optimal revenue question. So let me just show you one thing one can obtain from this. It's a natural question. It's saying that suppose I have something, I have a bunch of items I want to sell to a bunch of buyers who are financially much better off compared to another community. And the question is that, can I design the mechanism in such a way to extract more revenue for myself? I mean, seems to be a reasonable question. So this is called, is it monotone in distributions? And now, so if one distribution stochastically dominates another, does the revenue increase it? But Hart and Rennie show that quite unexpectedly, it's not true. So there are very simple examples, even for one buyers, where the that if you encounter some kind of, if you have some richer clientele, you might not be able to get more money out of them. And now, according to our paradigm, is this approximately true? And it turns out that one can show that this actually is true. That even though from the richer clientele, even though you may not be able to extract as much, but you would extract at least a fraction of it. Okay, so I will. I think that we are. So let me not go into this. So there are other things that the kind of, these are kind of central core questions in economics, and computer scientists also have been able to obtain from it. So let me just summarize this, that using the theoretical computer science technology, the contribution is that you can sometimes you can solve classical problems of interest as it is to economists, and also it gives a new angle for it. And one thing I did not say is that I think, to me, the most exciting part is now we have learned enough. We should be able to apply the mechanism design and the auction that we have learned through these 15 years. And now we can apply them to computer science problems, and especially things like blockchain. Okay, so the blockchain is the type of thing that saying that using our distributed computing system ability, we know how to construct a kind of certain body. It's just like constructing the physical characteristic of an animal. And now, if you play God, you say that well, what kind of ability should I give it? And now, the cryptography is something that we can endow the animal with. And then you say that, well, what is it good for? What do you want the animal to do? And that is kind of a value type question that we have turned to economics. And after we figure out what we want to do, the mechanism design will help us in designing it. And once we have a precise way to design it, we can use the cryptography to implement it so that it gets where it is. So that's the picture that I'm seeing. So I think I'm just going to spend a few minutes to just look at one small example how this come out. We have this blockchain we want to have, and in order to make it stable, we want to get fees for the parties involved in it. And how should we design it? Okay. So a blockchain is just growing list of blocks, each containing some certified transactions and linked together using cryptography. And if you enable it with decentralized, privacy-respecting method, then this will be really, really useful for the development in the future. And so the Bitcoin is the first serious and the initial rendition of the blockchain concept. So let me just show the specific technical questions that I have in mind. So you have users and miners, and users have transactions to be certified, and the miners create blocks to include this transaction in some way and collecting fees for each transaction. And for simplicity, let's just assume that there's one miner and there are a lot of users, and the users would bid the maximum they are willing to pay. So this looks like an auction problem. And the current way is to pay your bid, and you just sort everything and from top to highest to lowest, and then you just pack as many as possible until the block is full. But it's just like the first price auction. People tend to lie. And if you want to get more revenue for the miners, and it's important to increase revenue for the miners because these are the people who allow the system to function. Okay, so the monopolistic mechanism would be just like follows. You still sort the bids, and the miners will pick a K and take the top K and charge the winners the kind of the lowest value among this top K. And so the miners have the option of picking K. So would find the best K to maximize the revenue. For example, here, if you K equal to 3, you get $30. K equal to 4, you get 28. It turns out 30 is the best. Okay, so 30 is the so now, are the users incentivized to bid truthfully? The answer, I will not go through it, but if you look at it, you can find out that bidder 2, instead of bidding 13, if the bidder 2 bids 6, then he only have to pay $6, and so getting a 40% discount. So if you given this list of bids and let delta maximum to be the maximum discount among all the possible bidders, and that the miners would hope that this delta is very close to 0, so that nobody has the incentive to cheat. Experimentally, there's a paper by Lavi, Sattai, and Zohar last year, and they experimentally look at the many distributions and conclude the discount is very close to 0. And in the following model is kind of an independent generated over a finite range, and they give some indication why this should be so. And now this can be proved actually for any distributions of that sort, that is indeed for large n is close to 0. So it confirms the conjecture in the Lavie et al. Paper that NP is nearly truthful, and also shown to be robust against other attacks. And now it's possible to make it a strictly truthful mechanism. So I'm not going to go through it, but the answer is that if you make it truthful, then it actually you get a little bit less revenue, even though asymptotically it's about the same. And so this gives some indication that the monopolistic price mechanism is a good candidate. But the purpose of this is that I'm not suggesting this is something that you should do with the Bitcoin. It's saying that this is the kind of methodology, mathematical analysis, and that the mathematics is pretty fascinating when you try to do it, and then you understand that it's just looking from a theorist point of view. It's very interesting and challenging. This is sort of thing that Noga would solve for lunch, but not for other people. Okay, so now let me just conclude. I think that this is my finale, and so we are in a new age of computer science. In the previous 40 years, computer science is mainly focused on the internal development as a science, and that the impact felt by the outside seems to be limited to the computing power as perceived by the world. And in the new golden age, the computer science is coming out from the backstage and sharing the limelight with others like medicine, physics, chemistry as a transformer of the world. So this is good news, but it also is a responsibility and it's new challenges. So this is a new game for computer scientists. When opportunities arise, there will be winners and losers, and how you fare in it depending on what you choose to respond. And this new game, it's I think for both individuals and institutions, they need to respond to it. And for example, I firmly believe that the computer science research will be evaluated on the impact, at least to some part, that can be articulated and felt by others. And I mean that this will, I think this is probably already used by many leading institutions, computer science departments in the world, but it will become a de facto standard, I think, in future years, and not too distant future. And now, in this land of opportunity, the theorists have opportunities like never before. So you have a lot of things that you can do. And so, so to broaden our vision and think about what we would like to do. Now, lastly, kind of lifting ourselves from our own personal or institutions' interest, let's think about the world as a whole and the science and the future as a whole. I think right now it's really exhilarating time. The research breakthrough, where does it happen? As far as I can see, a large fraction come from the fusion of different scientific ideas. Some recent examples, the modern cryptography is really computer science plus information theory. The Fintech is about computer science and economics. The quantum computing is about computer science and physics. Now, what about the future? I think that as a theorist, I think my dreamland is that we'll have a coherent discipline in which our minds can run free, and all the theorists are equipped with all the mathematical techniques in order to choose any problems within this arena. So I think that the quantum, the neural, the AI, I think the neural is that Crystal is already doing it ahead of all of us. And I believe that some kid in the future will unify them all. Okay, thank you very much.
Questions from at some point in the talk you said MPC, with your knowledge of CPs, will rival the popularity of Bitcoin. Did you mean
No. I personally don't like cryptocurrency as the way it is, because it's completely anonymous and really, I really cannot think of any good use of the current vision of the cryptocurrency except for kind of for gambling and or ransom. Yeah, right. That's right. But I think that cryptocurrency does have a future from the governments, from the because it makes things more efficient, and also it will track the financial transactions much more easily. So that, for example, the U.S. I think that the U.S. can drop many of the kind of funny regulations and just rely on technological means. So I think that the cryptocurrency it's just a part of it. I think the main thing is the blockchain and perhaps some other distributed system ideas will have the benefit of more efficient and actually more secure. And when you endow it with the mechanism design and with the cryptography, I think it will change the financial world, and I believe that we'll see it happens really soon. I think first is the making the crypto practical, and with the tools available, then I think people will can focus on how to use them in the appropriate ways. Thank you very much.